I am very happy to introduce Professor Negar Elhami-Khorasani. So Negar is an associate professor at the University at Buffalo, and she will tell us about tunnels.
Thank you, Thomas. And hello, everyone. Before I get started, just a few quick notes. It's very exciting to see all these presentations today, and I just want to thank Thomas for organizing this event. And a quick second note that earlier today, as part of the first set of presentations, we heard a real tunnel, basically, case. It was mentioned as part of an airport infrastructure. And then later on, there was a full presentation as part of UGANT and Dr. Ruben Van Kooij's group. So there are definitely, differences with what I'm presenting here, but it's really nice to see that we have perhaps similar conclusions, and I will also show how we use SAFIR from different perspectives in this project, and definitely the tool performed well and provided good results for us. So this presentation, also a few of you might have seen it already, but the way I'm presenting it today, again, I'm perhaps not going in detail for every aspect, but showing different application of SAFIR as overall part of the project. So the motivation for this research was basically looking at realistic tunnel fire events, and the two pictures here show two historical events, and extensive fire spreading occurred in both fires. These tunnel fires do not necessarily lead to the collapse of the structure, but they definitely cause damage along the tunnel. And these fires can last for hours or even days. So they can damage hundreds of meters of the tunnel liner and then cause huge economic losses. This damage assessment procedure, what I have here in the flow chart, it's basically what we can extract out of the US guidelines. We typically start with visual inspection, some non-destructive testing, sampling of materials, and there will be some guidance on damage classification and repair classification. But most of the time, in practice, it will be done, ad hoc basis. They make decisions. Now, what we, as part of this project, what we want to show is that as in this flow chart, it can be updated and advanced modeling and analysis be inserted into the process. If we can recreate the fire scenario, we can analyze what happened in the structure and what kind of deflections, what kind of stresses within the structure got developed, get the temperature, structural response, and with that, with all the other things that they've done with visual inspection, non-destructive testing, get to the damage, and then decide on repair. As a side note, this process with advanced modeling can also be used for design. So that's for sure. So why did we choose SAFIR as part of this work? Because we know it would be efficient for us in terms of modeling, and it would give us the capacity to perform parametric study and run many simulations as opposed to other tools. So the talk has three parts. The first part is looking at modeling large-scale experiments of reinforced concrete tunnel slabs under heating and cooling phases of fire. And then the second part is completely different. It's looking at evaluating a performance of tunnel sections under fire, considering soil structure interaction. So now we're bringing the geotechnical side of this into the picture. And the last part is short, like just 2-3 slides. It was a topic kind of was brought up earlier also in terms of how to incorporate spalling when we want to evaluate damage in these tunnel slabs. So going through the experiments, here is, I will play a video and I'll talk over this. So these fire tests were conducted using a furnace at the University at Buffalo. The test setup, here you can see it, the center bottom surface of the slab was exposed to heat. And then an actuator is loading the slab from the top with a spreader beam that's basically mimicking the soil load that's being applied to a tunnel slab. You'll see shortly that these slabs were post-tensioned to mimic the restraint provided by the surrounding tunnel sections in a real case. And these are some thermocouples. We had temperature measurements. This is a view from inside. This is just a steel mesh in case we experience spalling. We didn't want to damage the electric coils inside the furnace. This is the post-tensioning strands I mentioned. And this is just the data acquisition system. And we measured both displacements as well as temperatures during the test. Okay, just going to move on. There you go. So we overall, here's our test matrix. We had a few tests. Specimen S1, that's the first line. And I will come back to that one later, is the control specimen, which had 6 post-tensioning strands. It included polypropylene fibers. Basically, at the end, it didn't spall. Specimens S1 was tested using scenario 1. Here's the fire scenario. This fire had a heating rate of 40 degrees Celsius per minute. Maximum temperature reached about 850 degrees Celsius, and it was kept at that temperature for 60 minutes, and then it followed natural cooling. Now, the parameters changed for the other tests. So in the second test, the number of strands changed. The idea behind that was the level of restraint in different tunnel sections. If you have a horseshoe, you have circular, you have rectangular, that would change. Then the test 3 and 3B, they're similar to test 1, except they have a different fire scenario. So here you see scenario 2 and scenario 3. This is a very quick fire. You see it just heats up and then basically fires out. So this is testing here in the US. When we're studying this, there was another study, parallel FHWA, Federal Highway Administration Association. They basically said, what if we use fixed firefighting system inside the tunnel? And they were looking into that from safety and evacuation. This was just, our project was focusing on structural performance. So the idea was that if they have fixed firefighting system, there should not be damage because the fire just quickly goes down. And we modeled it, we tested it. It was, yes, well, again, I'm going to show that. And then eventually, because the slab didn't really get damaged, we introduced, after 2 hours, it was completely cooled down, the same slab, to this, what we call traveling fire, where the heat approaches our slab. It's like the fire happened somewhere else in the tunnel, and then it moved and reached the slab, reached 800 degrees Celsius, and again, cooled down afterwards. Test 4 is concrete without polypropylene fiber. Considering the time, I'm not going to show the results for all of them. I will only show test 1 and 3A, where you have actually differences in temperature. This one didn't get exposed to high temperatures. Okay, this is the specimen. So these specimens were designed and constructed using similar reinforcement design and similar to realistic as much as we could to tunnel sections. The cylinder test gave us a concrete strength of 66 MPa and 73 MPa with fibers and without fibers. And we had, as mentioned before, several thermocouples distributed inside the specimen to get the temperatures. So getting into actually SAFIR modeling, we considered different approaches, beam, shell, and solid. We totally understand that considering that it's a slab, considering longitudinal transverse performance and behavior, the shell element should perform well, but we just wanted to see that considering the level of complexity here, we wanted to try all 3 approaches and see what we would get. And we are talking, in terms of computational effort, we are talking about minutes here with the beam section versus it took us hours to run on a regular computer, no high performance computing here. So minutes versus hours. And in this case, it actually got to days, past 24 hours to run these simulations. So that's another thing to keep in mind. The beam model adopted 2D heat transfer. And as you saw in the setup, there are parts of the slab that's sticking out from the main chamber. So there's the cooler part, and then there's the primary part that's actually being heated. So you consider that cool section versus the section that got exposure to heat. The shell elements adopts 1D heat transfer, and then the solid elements, solid model included 3D heat transfer. Okay, so in terms of post-tensioning, so we couldn't define contact property. So these are unbonded. So I forgot to mention this. So in the test, the post-tensioning, they're unbonded. So rather than directly modeling the actual ducts and post-tensioning strands, we considered again 3 different alternatives. And we know that these ones, this basically 3 approaches will give us an upper bound and lower bound of what would happen in reality. The first method uses an embedded, basically, or it would embedded in concrete an element that represent a bonded strand. It would look like that. And the second method uses a post-tension truss element that would connect both ends of the slab, so here and here. And the third method applies a horizontal force along the center line at one end of the slab. Now, this force, this is not predicting, this is actually using the measurements we read during the experiment and define. So this force actually changes with time based on actual measurements during the test, and we just want to see how that would work. Obviously, this one, because it's bonded compared to what we had, would have higher stiffness, maybe slightly less deflection. And this one is the truss element. Because this deforms, whereas this truss element stays where it is, then there would be some extra moment induced. And finally, this here again, the location of that load that's being applied is not changing, so there would be some extra moment as well here. In terms of these are some results. In terms of temperature, upfront, I'll mention that similar results were obtained from 1D, 2D, and 3D thermal analysis, considering the 3 different methodologies. It makes sense mainly because of the way that the heat was uniform and the slab, was symmetric, and so it made sense. We would get similar results. This is results from 2D heat transfer for test 1 and test 3H. So test 1, we reached 850 degrees Celsius. You see that at 25 millimeters. So the dash is SAFIR, and these they're dots, basically measurement readings, but we had a lot of readings. So this is the experiment, that's the experiment. Again, these are the experiments. There might be a little bit of difference at some points, but overall we were happy with these results. One reason for the difference, so number one, we did not calibrate, we did not change any material properties. These are the default material properties in SAFIR. And then another thing I should mention, that these were relatively large specimens. So we actually had a concrete truck on site, and during pumping, so these thermocouples were attached. But it was, they were pumping concrete, and we are aware that maybe we couldn't really control. Some of the thermocouples might have moved a little bit, maybe a few millimeters, considering the pressure of those concrete pumps. So bottom line, looking at this, all the differences less than, I would say, 80 degrees Celsius. That was the maximum error we had in all of our simulations. So this worked well. Now moving on to results for displacements. This is center line displacement. Now I'm only showing heating. I will, in the next slide, include cooling. Another point I want to mention, which is going to show up on the next slide, is that here the displacement is zeroed at the beginning of the fire. We know that we applied the load, So the displacement due to ambient, the load at ambient temperature is not included in here. Okay, so the beam elements, number one, let me clear one thing out. So we have bonded, truss, lateral force. These are the three versions we use for post-tensioning. You see that, and these are beams. Dashed lines are shells. Dotted line is actually the test, and this blue dot is the solid model. And you see the bundles here. Basically, the way that we consider post-tensioning really didn't make that much of a difference, partly because maybe the level of post-tensioning was not to the level that really created, it made an impact, but not to the point that the way that we modeled it came, make a difference. The beam elements definitely between, this is test 1, 3A, didn't perform well. We kind of expected that. Couple of millimeters of error. The shell element is definitely doing well, as expected. And then the solid element, it kind of stops here because we tried variations of this model. Again, wanted to see what we would get. We had convergence issues, and the convergence would show up when elements as part of the system, as part of the whole slab starts going through cooling. That's when the model stopped converging. So once we experienced some reversals, then the model had issues with convergence. Okay, now I want to show you the centerline displacement with full duration of the fire, including cooling. So goes up to 24 hours. I am also not zeroing the displacement at ambient. So you see that's one thing that the model has a few millimeters. It's not, basically the model is stiffer than what actually the slab experienced at ambient before the fire started. But if we remove that, I just wanted to show it to you, but if we remove that, and not look at the ambient, but we have the load, then have the fire, the shell element actually does pretty well. So this dots, blank dots, is the test, and the dashed lines are the shell elements. So the shell element actually captured the cooling pretty well. This jump that you see here at the end of the day inside the laboratory, we had to remove the actuator for safety reason, and then let the concrete cool. So this goes up to 24 hours after the test. So overnight it was cooling, but we had to remove the load. And in the model, we also removed the load. Okay, so moving on. Now I want to quickly talk about, have a few minutes, talk about two more applications. So first one, this is soil structure interaction. Completely, switching gears. Here we are looking at schematics of 4 bored tunnel sections. These tunnel sections, so 1 and 2 are in soft soils, while tunnel section 3 and 4, they're in hard rock. So we're looking at the effect of basically technical condition. And if in tunnel section 4, it's not only in rock, considering the depth, it's actually subjected to large lateral forces from the surrounding rock. These 4 tunnel sections were modeled in SAFIR. This time we used beam spring models, where the reinforced concrete liner was modeled using beam elements, and the subgrade section was captured by a series of spring elements. Only half of the structure was included in the model using symmetric boundary conditions. The applied loads included earth pressure, water pressure, live loads, and self-weight. And 2 separate analyses were conducted for each case using wrapped fire with a cooling phase, and then an RWS without cooling. And I'll come back to this, why we ran it for 100 hours. We had a motivation for that, and that the results, I'll mention it. And only top half of the tunnel here, it was exposed to elevated temperature, and the model considered all temperature-dependent properties of concrete and steel and so on. One thing I want to quickly mention, again, considering the time, I'm not going to go into details, but this time at ambient temperature, we wanted to verify this spring models here and the geotechnical consideration. So when we designed these 4 tunnels, we modeled it in SAFIR. We analyzed them using elastic equations basically that are available out there. And then the third one, it was another software, FLAC 3D. It's used by geotechnical engineers to get forces. And the three approaches gave very reasonable, very close, and SAFIR did pretty well, ambient, no fire. So it gave us confidence that, okay, we can move forward with this and analyze under fire. So that was basically the idea. So I am not going to go into the details, but basically we all know, based on everything we heard earlier also this morning, there are reversals on moments in all these sections as we go through heating and cooling. So this is a whole summary of the results for the 4 tunnel sections, and it included the maximum moment axial force. Residual ovality is a measure for tunnels that basically gives us an indication of how much the whole section, like is circular versus oval, like how much is deforming, rebar temperature and rebar stresses. And you get them for ambient and heated, and then the delta, the difference. So in 2 of these tunnels, none of them failed, by the way. This is rapid fire. Moderate versus deep tunnel rock and moderate in soft soil. These 2 cases, the rebar yielded. And in moderate depth tunnel, what's happening in soft soil is actually it's yielding, and it's mainly because of deformations, large deformations. So this case experienced largest deformations, whereas in deep tunnel in a rock, you don't get deformations because you're in a rock section. But because you can't release those deformations, then they're built up of forces and moments that lead to yielding of the rebar. So these 2 cases here kind of gave us an indication that they might be critical. Now, we analyzed these 4 tunnel sections for running for 100 hours of RWS fire, because we got this question from the fire department. I know it's 1:51, so I'll be done in like 2 minutes. Thank you. So the fire department asked us if it fails, for the safety, like because these tunnel fires can go for hours. They said, how many hours can we assume that there probably no collapse? And so that we can get the fire crew in and so on. TS1 and TS3, shallow and soft and moderate depth in rock, again, did not fail at all, 100 hours, whereas TS2 and TS4, so the geotechnical condition makes a difference, 45 hours and 52 hours, one runaway failure at the crown, the other one runaway failure at the spring line, they actually experienced collapse. Finally, 2 more slides. We wanted to also get spalling into this damage assessment process, as I started motivation of this. And Ruben did a great job explaining this, so I'm going to go really quickly. But basically, what we had done is we came up with, you need to get the spatial distribution of temperature across the tunnel. And then you have, we came up, it's a simplified approach, we get it, but it's better than perhaps nothing. So at some time, the spalling starts, there's a linear rate of spalling, and then when it gets to the cover, for example, full cover, then it stops. So we had this routine MATLAB SAFIR interactive program to automatically take care of this. Basically, at each time step, once the spalling occurs, you have a layer of that concrete. So you want to have a fine mesh. These will get removed, and then the fire exposure. So this would be a new section where the fire will be exposed and the heat will penetrate quickly. It makes a difference. There's in the literature, if temperature threshold exceeding 300 degrees Celsius, it means that it needs repair or replacement. So just based on heat transfer, not even going into structural analysis, without spalling, we ran 540 cases of fire scenarios in a tunnel. This was part of like parametric study synthesis, 540 cases. So this is like a distribution of the type of damage we get. And just as a comparison, the maximum level of damage you would get of all these scenarios with spalling is 226 cubic meter of concrete that needs to be replaced, whereas 142. So with spalling, obviously we get more damage, so it might be a more realistic, or maybe depending on the accuracy of the model, we know it's not the best and it's a simplistic approach, but it gives us, again, an idea of how much the spalling could make a difference. So in conclusion, very short, we started with the idea that advanced modeling can be used for both design and damage assessment. And this basically research confirmed that definitely models such as SAFIR can be used to guide such processes. Thank you so much. Sorry for going over time.
Thank you very much, Negar. Thanks a lot for this great presentation spanning different efforts on modeling of tunnels. Very interesting. We do have a question on the first part and the modeling of your experiments conducted at Buffalo. If you wouldn't mind going to the slide 12, I think the question was on the displacement profiles. Yes, thank you. When for test one, let's say when you ran the test for 24 hours, could you please comment on where the fire stops and then where you remove the load you mentioned, but
right.
quickly and explain how that is linked to the displacements you observed.
Definitely. So a very good question. I'm going to go back and here's the fire curve. So this is up to 12 is like completely cool at this point. So this is the fire curve. It gets to 850 and then we keep it. So slightly more than 1 hour. The overall test takes less than 2 hours. So that's when the furnace is shut down. Right, but the furnace is shut down, but the door of the furnace is not open yet because it's really too hot. In about 4 hours, this is like when you see this drop is when we open the door of the furnace. So if you look at this, if this is 6 hours, 2 hours, you do actually see, we have zoomed in versions in our publication, you would actually see, because the heat's still penetrating, so end of the fire obviously is not where you get the maximum displacement. Heat's still penetrating inside concrete. 4 hours, we open the door, but the concrete's still sitting there. We slightly open the furnace door just to get some air basically in. And then when the load is removed is here. It's almost close to 6 hours because we started these tests about 9 a.m. The lab would close at around 4 p.m. Just before, a little bit before the lab closes, we remove the actuator load. Here, that's why you see that jump. Here it is. Here's the jump. Here's again the jump, and that's when the load is also removed. I hope I addressed that question.
Yes, thank you. And so based on since we are on that plot, could you share your thoughts on the beam versus shell models and so what you observed?
Yes. So the idea that a few minutes model, like running these beam models were very quick and very super easy, but perhaps the accuracy we're getting, and again, we knew it's a slab, the way that the slab performs. So at the end of the day, we did not recommend using a simplified beam model to capture the displacements. And obviously the solid elements, because of the cooling, we had some issues. But we were very much happy with the way that the shell elements worked. To be exact, this kind of model is actually not too bad the way that I'm presenting it. Just I need to be honest. It took the mechanical model for shell elements ran for 2 hours. That's it. So they're actually pretty efficient to us. So our recommendation was the shell elements perform really well in heating and cooling and provides good predictions. So that's the way to go.
Very good, thank you. One last question from Chenji. It deals with the end of the presentation when you quantify damage and the number of trucks needed and so on. Could you remind us or specify the damage criterion or how you defined the quantity of damaged concrete?
So in this case, it was just purely based on heat transfer. We did not introduce, I mean, the slide I'm showing basically, just based on heat transfer, so that here people are comfortable running these analysis. Any concrete, it's based on, some literature I provide here, Concrete Society, FHWA, FIB. Any concrete above reaching threshold of 300 degrees Celsius, it does undergo some chemical changes. Therefore, for the purpose of repair, they would rather replace that concrete. in practice. So the criteria here is the volume is calculated along the tunnel. So this 540 scenarios, we use high performance computers, but these are all FDS simulations. So we ran all those simulations. We got distribution of temperature along the tunnel length and along the cross section at each point. And then we calculated performed heat transfer analysis using SAFIR. And then we got the volume of concrete that exceeded 300 degrees Celsius.
Thank you. Thanks again, Negar. Thanks a lot for your contribution, your presentation, and the Q&A.